Okay, so we're going to start talking about molecules and molecular compounds. We've talked about atoms and about the different particles that are inside of an atom. A molecule is when you have two or more atoms that are basically stuck together. The thing that holds them together is called a covalent chemical bond. We're not going to go over what that is in this class. So we'll talk about what those chemical bonds are in Chem 1A. We're not going to go into that. For now, I've talked about Lego blocks being stuck together. The covalent bond is the little posts and holes that causes them to stick together, right? So the atoms in a molecule can be atoms of the same element or of different elements. If the atoms are the same element, then the molecule is still an element because it only has atoms of one kind of element. If you have two or more different elements present in this molecule, then it becomes a compound. So a molecule can be a compound or an element. Now, a diatomic molecule, this prefix di means two. Diatomic literally means two atoms. This is a molecule that has two atoms in it. So a molecule like H2 has two hydrogen atoms in it. There are 7 elements that when they are found as free elements are always diatomic. And these are ones that you should know. And there's a mnemonic, a sentence, where the first letter of each word has significance. Horses need oats for clear brown eyes. So those 7 elements are hydrogen. So if you see hydrogen all by itself, it's always going to be H2. I think of these elements as the junior high girls of the element world. I don't know if you remember back to junior high. When I was in junior high, we had a speaker come to a rally or something, and he pointed out that junior high girls never go to the bathroom by themselves at school. You always say, I need to go to the restroom. And a friend goes with you, right? That even happens with adult women a lot in a group at a restaurant. You don't go by yourself, you take a friend. Not sure why, but we do it. So these elements, and there are scientific explanations for why they do this, but these elements always take a friend. So you don't find free hydrogen atoms running around. You always find a hydrogen atom with another hydrogen atom. Think of them as holding hands and they're strolling through the world. So hydrogen does that. Horses, H for hydrogen. Nitrogen does it for need. Oats, that's oxygen. 4, that's fluorine. Cl is chlorine. Br is bromine. And then the I's part, nothing ever works out perfectly. That's iodine. So those 7 elements. Okay, so they always make diatomic molecules. 2 atoms of the same element stuck together as a molecule. And then, so those would be homonuclear. Homo is a prefix meaning the same, nuclear referring to the nucleus. So the same nucleus, so 2 atoms of the same element. A diatomic molecule, 2 atoms of the same element. Hetero is a prefix meaning different. So a heteronuclear diatomic molecule contains 2 atoms of different elements. So here we have an illustration of a homonuclear diatomic, a heteronuclear, and then we could have polyatomic. Poly is a prefix that means many. So polyatomic means many atoms, more than 2. Any questions? Well, a chemical formula gives us the composition of a substance. It tells us what elements are present and their relative quantities. There are different types of chemical formulas. A molecular formula shows the number of atoms of each element in a molecule. It's the formula for a molecule. So if the molecule has 2 hydrogen atoms, then the formula will be H2. We use subscripts to indicate the number of each kind of atom. And we never write the subscript 1. You'll see as you learn more about chemistry that chemists seem to have a thing against the number 1. We don't write the number 1 unless we have to. I think it's more about being efficient and not writing extra junk down, but we don't write the number 1. So you're probably familiar with the formula for water. What's the formula for water? H2O. So H2O. It's not H2O1. We don't really need the 1. If there are no oxygens, we just don't write the element symbol, right? If there's 2 or 3 or 5 oxygens, then we'll put a subscript. So just writing the O tells us there's 1 of them. There's a 2 after the hydrogen because there's 2 hydrogen atoms. These are subscripts. The subscripts are smaller numbers, and they're kind of sunken down like a submarine goes under the water. The superscript is like Superman and flies over. So it's important to get the size of your letters and numbers appropriate. We could have, NH3, H2C2O4. These are all examples of molecular formulas. Any questions? A structural formula gives us information about the structure of the molecule. How are those atoms connected? So here is the molecular formula for water. That doesn't tell how those 2 hydrogens and the oxygen atom are connected to each other. It just tells us how many of each are there. These are examples of structural formulas because they show the connection. They show that the oxygen is in the center and the hydrogens are on each side. There's other possible ways that you could connect those things. You know, you could put the hydrogens next to each other and stick the oxygen on the end. That's not correct, but you could guess that just from the molecular formula. Or you could say, well, they're playing ring around the rosy and it's actually this triangle thing. Okay, neither of those is correct. But these structural formulas give us that information. So we said earlier that molecules are atoms held together by chemical bonds. The chemical bonds are most often represented as a line, but they're sometimes represented as dots also. And you'll do more with dots in Chem 1A. These are models that also give structural information, the ball and stick model and the space filling model. Any questions? Well, if we look at a model of a molecule, we should be able to figure out what its molecular formula is. So here, this is ethanol. This is a ball and stick model of ethanol, and they want us to write the molecular formula. So the colors here indicate which element that atom belongs to. Now, I don't expect that you have memorized those, so I'll tell you that red is oxygen, and white is hydrogen, and black is carbon. Well, which one do you want to start with? Black. Okay, so black is carbon. So there's 2 carbon balls there, 2 black balls, right? That means there's 2 carbon atoms. And so I'm going to write the element symbol for carbon, followed by the subscript 2, because there's 2 of them. How about hydrogen next? How many white balls are in the picture there? 6. So this would be H6, and then there's 1 red one. Red is oxygen, so I just write O, not O1, just O. So that is a molecular formula for ethanol. Yes?
What if someone rearranged differently?
It could definitely be arranged differently. You might see this written as CH3, CH2O, OH. That gives more information about how things are connected. At this point, if you wrote OC2H6, I would still count that correct. There is actually a particular order in which we write the elements, but I don't see any point in getting into that. This still tells us the number of atoms of each element, and that's what we're interested in at this point. Any other questions? So this formula just tells us what the building blocks of that molecule are. The molecular formula tells us I need 2 red Lego bricks and 5 blue ones or whatever. It doesn't tell me how to put them together. Originally, compounds were given names in somewhat the same way as people are given names. A lot of names have meanings, right? Compounds were given names based on maybe their properties or where they came from or what they looked like. Methanol was originally called wood alcohol because you could make it from wood. And so there's a lot of these common names. But we now know that there are we have millions of known compounds. And so having common names doesn't work anymore because there's just too many compounds. So we need names that are more descriptive of the compound. Some of those common names are still in use, but all chemicals also have a systematic name. And the fancy word we use for a naming system is nomenclature. So nomenclature is just a system of naming compounds. There are different categories of compounds, and because of the differences between those categories, different systems or different sets of nomenclature rules are appropriate for them. So these are 4 broad categories of different compounds. We have binary molecular compounds, we have ionic compounds, there are acids, and organic compounds. And we're going to look at how to name the first 3. We're not really going to go into the organic compounds. The textbook touches on it a little bit, and that's about as deep as you'll go even in Chem 1A, and so you won't have any trouble with that when you get to Chem 1A. This is the part that you really need to have some understanding of before you get to Chem 1A. So first we're going to look at the molecular compounds. A binary molecular compound. Binary means 2. So this has 2 elements. Just 2 elements. So to name a binary molecular compound, we first are going to identify the 2 elements. What are they? Then to write the name, we write the name of the first element first, and then you write the name of the second element. Okay, so far so good. But we don't want this name to look like it's just a list of element names. We want to identify it as a compound. And so we take that second element and we change the ending of its name to "ide." So if it was nitrogen, it becomes nitride. If it was phosphorus, it becomes phosphide. And then to indicate how many of each atom there are, we're going to use Greek prefixes. There's a set of Greek prefixes that indicate numbers. So we put the prefixes go before, right? That's what pre means. The Greek prefix goes before the element name to indicate how many atoms of that element there are. Now, the prefix mono means 1. Well, I told you, chemists have a thing against the number 1. We also avoid using the prefix mono unless we need to. So the prefix mono is almost always omitted for the first element. And it is sometimes omitted for the second one. So here are the Greek prefixes. Again, don't use mono on the first element. So these prefixes, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. You may recognize some of these from geometry, right? A pentagon has how many sides? 5. Penta is a Greek prefix that means 5. An octagon has 8 sides. Nonagon, you maybe don't remember that one, but at least nona sounds like 9. Deca, how many years in a decade? 10. Deca is a prefix meaning 10. A triangle has 3 sides. The ones that might be a little odd are tetra and hepta. Okay, tetra and hepta, those might be new. Now, a lot of these prefixes end with an A, and mono ends with an O, and so we often drop that last letter when we're naming an oxide, just to avoid awkward words. Like monooxide ends up looking like monoxide with a double O in there. It looks funny. I am not going to try to trick you with that, okay? Most of the nomenclature things where you'll be tested will be multiple choice, and I will not try to trick you with those. I tell you about this dropping that last letter because I don't want you to be confused. Why is there an A here and not over here? It's because we do that. I'm sorry, it should be more consistent, but it isn't. So let's practice naming some compounds. So if we look at this compound, how many elements are in it? 2. This is a binary compound. The other thing about binary molecular compounds is that they are 2 nonmetals. We're going to also talk about ionic compounds. If there's a metal in it, you can't use these rules. So here we have 2 elements. What are they? Carbon and oxygen. So we've got carbon and we've got oxygen. Whoops, oxygen. Okay, so we write the name of the first element first, carbon. How many carbon atoms are there? 1. Do we put mono in front of it? No. And then we take the second element and we change the ending to "ide." So oxygen becomes oxide. How many oxygens are there in the molecule? 1. So we're going to say monooxide, but that looks funny. Monooxide. Doesn't that look funny? Looks funny to me. There's double O's. So this is where we often drop that O. So monoxide. You've probably heard of carbon monoxide. Odorless gas, toxic because it prevents you from getting oxygen. What about this one? This one's also 2 elements. The same 2 elements. But it's a different compound. This one has 2 oxygens. So instead of carbon monoxide, carbon and 1 oxygen, this is carbon dioxide. You don't want to drop the I. We only drop the A or the O. We don't drop the I in di or tri. So carbon dioxide. We have to have a unique name for each chemical, for each different compound. You can't have 2 compounds with the same name. It gets very confusing. I had 2 students in a class once with the same name. Same first name, same middle name, same last name. That was confusing, right? So we had to use a nickname for one because it was just too confusing. Well, here we have control over all of the compounds, and so we've decided everything's going to have its own unique name. And that's why the system is the way it is. Any questions yet? How about Br308? What are the 2 elements in there? Bromine and oxygen. So this time the first element, there's more than 1. There's 3 of them. What's the prefix meaning 3? Tri. So tri-bromine, the first one is just the element name with a prefix, and then the prefix for 8 is octa. And here we have that prefix octa and an oxide, and so we're going to drop the A. What a minute, wait. Okay, octoxide. It still ends up seeming strange, but there it is. Now, if I was giving you a written exam and you wrote tribromine octaoxide, I would not count that incorrect, because even some chemists disagree about when you should keep the A and when you should leave it off.
So when you drop the A, it always goes to O?
Well, what we're doing here is we've got oxide. That's if we didn't drop anything. And it's generally with oxide, because oxide starts with an O and we end up with these weird vowel combinations. And so we'll just drop that out because we still know what it means. It's just easier to say octoxide instead of octaoxide. It's weird. So what would the name of this one be? Phosphorus pentachloride. Phosphorus pentachloride. Questions? Students usually don't have too much trouble with these guys. How about this one? NF3, what would that be named? Nitrogen trifluoride. N for nitrogen, we don't need mono on it. And then trifluoride. Students misspell fluorine a lot. Fluorine is F-L-U-O-R-I-N-E. And the common misspelling is fluorine. There's no flour in fluorine. Fluorine is gluten-free. Okay, no flour in fluorine. I know what you mean, but I'm going to snicker at you when I grade your paper. Okay, what's this one? N2O4. Dinitrogen tetroxide. So there again, we're probably going to drop the A and just say tetroxide. Now, depending on which instructor you have for Chem 1A and what textbook they use, it might show up as tetraoxide. That is one of those details that I don't think is worth arguing about. I'm going to say I've got lots of other details that I will argue about, but not that one. Well, what if we have the name and we need the formula? Is it just the reverse? You're going to write the element symbols in the same order that they were in the name. There actually is a specified order, just so you know. But because you're going to be given either the formula or the name with the correct order, I don't think we need to bother you with trying to remember that. Write the element symbols in the same order as they appear in the name, and then use the prefixes to get the subscripts. And again, we never write the number 1 in a chemical formula. So a couple of examples here. Sulfur tetrafluoride. Well, what's the element symbol for sulfur? Capital S. Oh, I should select the writing tool. You'd think I'd know that by now. How many sulfurs? 1. There's no prefix, and we need no subscript. There's one of them. And then fluoride. What's the symbol for fluoride? Fluorine is F. Okay, did you see I put something up on Blackboard that's a list of things you need to memorize? Did you see that? A bunch of element names and symbols. Well, so do your best to memorize those, but then you can also use strategic guessing, right? So fluoride, a good guess would be the first letter or two of the name. So you might be trying to decide between F and FL. Well, check the periodic table. Is there an FL on the periodic table? No, there isn't. So that can't be correct, right? So then probably go with F. Sulfur, tetrafluoride, tetra means what? 4. So SF4. What would the formula for tetraphosphorus decasulfide? P4, phosphorus, tetra means 4, and then sulfide again, it's not very creative, and deca means 10. P4S10. Of course, there have to be exceptions. I told you yesterday that hydrogen, I think of hydrogen as the baby brother of the element family. He gets away with breaking lots of the rules. That happens with nomenclature also. Molecular compounds containing hydrogen are often referred to by their common names. And you'll see inconsistencies about whether hydrogen is given first in the name and in the formula, or it comes second. And just accept it. It's hydrogen. He's cute and little, and we just have to deal with it. I have older children, and I have a 7-year-old, and he has these big brown eyes that are like liquid chocolate. And he just, he gets away with stuff because he turns on his cuteness. And what are you going to do? So hydrogen is like that. He just gets to do things his own way sometimes. So of those funky compounds, you need to know 2 of them. You already know one of them. Water. H2O. The molecular name for it would be dihydrogen oxide, but we never call it that. But you can scare people if you want. My teacher made us drink dihydrogen oxide today. I think I'm going to die. Right? People, oh, freak out. It's a chemical. Yeah, it's a chemical, and if you don't drink it, you're going to die, right? It's water. We always call it water. And here's another molecular compound containing hydrogen that we do not call nitrogen trihydride. We call it ammonia. So you need to know those 2. And here we have this, in this compound, the hydrogen comes first, and in ammonia, it comes second. Why? Because it's hydrogen. Okay? And then there's a whole big group of chemicals that are classified as organic chemicals, and they contain carbon and hydrogen. They have a whole nother set of naming, because this system for the binary molecular compounds is too simple for all the complexities of how they go together. And we're not going to worry about that in this class. Okay, we're talking about hydrogen brings us to acids. There are several definitions of what an acid is. The one we're going to use is, an acid is a substance that produces hydrogen ions when dissolved in water. So several of the binary molecular compounds are going to fit this description. Examples would be like HCl or HI. These are 2 elements, right? 2 elements, it's a binary compound, they're both nonmetals. And so this can be named as a binary molecular compound, but it also is an acid when it's dissolved in water. And so we name it as an acid when it's dissolved in water. I think I've got, yeah. Okay, so here's what we do to name it as an acid. You shorten the first word, hydrogen, to hydro, and then you change the ending "ide" to "ic" plus the word acid. So let's look at these 2 examples. This AQ in parentheses after the compound formula is meaning that it's dissolved in water. So what most people will tell you is If it's aqueous, if it's dissolved in water, name it as an acid. If it is not dissolved in water, then name it as a binary molecular compound. So let's look at HF. If we had HF with no indication of it being dissolved in water, we would call it what? Hydrogen fluoride. You might say, well, why not hydrogen monofluoride? Well, that's a good question. Because there's no other compound between hydrogen and fluorine. With carbon and oxygen, there's CO and CO2. And so we need carbon monoxide to distinguish it from carbon dioxide. But with hydrogen and fluorine, there isn't. And so that's why we drop the mono. I'll write it in there, though. I would not count it wrong if you wrote monofluoride, but hydrogen fluoride. So if we dissolve this in water, it becomes an acid. And we're going to name it as an acid. So then we take this hydrogen and we shorten it to hydro. So we're just getting rid of this gen part. We're cutting that out. And then over here, fluoride, we change this "ide" ending to "ic" acid. So, and we run it all together. Hydrofluoric acid. The only binary molecular compounds that can be acids start with H. They all start with H. So let's look at HCl. How would we name that as a binary molecular compound? Hydrogen chloride or hydrogen monochloride. So that would be hydrogen chloride, the name of the first element, the name of the second element with the ending changed to ide, hydrogen chloride. If we dissolve this in water, it produces hydrogen ions. It's an acid. So what does the name become? Hydrochloric acid. Any questions? And again, this is another place where I'm not going to try to trick you. There are places that I'll try to trick you, but I'll tell you about them. I'm not going to try to trick you about this, about whether you name it as an acid or a binary molecular compound. The important thing is that you know how to do both. Try to remember that if it's aqueous, if it's dissolved in water, name it as an acid. Okay, any questions? Okay, empirical formulas. So we've talked about molecular formulas and structural formulas. An empirical formula is the simplest chemical formula. It gives the smallest whole number ratio of elements in a compound. The word empirical means from experiment. These are formulas that we get from experiments. A molecular formula is the true formula. The empirical formula is the simplest formula. And I think this is one I got interrupted when I was writing. I meant for simplest to be in italics and true to be in italics, and I meant this to be in bold. Oh well. So let's look at a couple of examples. Hydrazine has been used as a rocket fuel. N2H4, that's the molecular formula. Every molecule of hydrazine has 2 nitrogens and 4 hydrogens. Is this the simplest ratio of nitrogen to hydrogen? No. The ratio here is 2 nitrogens to 4 hydrogens. 2 to 4. That can be simplified. We can divide both of them by 2 and get a ratio of 1 to 2. So the empirical formula for hydrazine would be HN2, backwards. N2, sorry, NH2. It's a little bit like a fraction here. 2/4 could be reduced to 1/2. So this is the empirical formula, and this is the molecular formula. Benzene. That's an organic compound. It's got a special name. Benzene's molecular formula is C6H6. What's the empirical formula? Just CH. That gives the simplest ratio. Empirical formula doesn't always give a whole lot of information, but it's what we get from experiment, and then we have to do another experiment to figure out what the actual molecular formula is. So write empirical formulas for the following molecules. Molecular formula for glucose is C6H12O6. What's the empirical formula? CH2O. Those subscripts, 6, 12, and 6, are all divisible by 6. And so we get 1, 2, and 1. Adenine, C3H3N3. CHN. I'm looking at the subscripts and I'm finding what's a common factor that I can take out. Well, they're all divisible by 3. Nitrous oxide, that's laughing gas. If you go to the dentist, and they may give you nitrous oxide. What's the empirical formula for that one? It's the same as the molecular formula. A ratio of 2 to 1 is the smallest ratio. So this one's N2O. Sometimes the empirical and molecular formulas are the same.